All right. I'm going to pick up right where we left off with linear programming. If you recall from way back when, I hope everybody had a really wonderful long weekend with relatively little work. I definitely did very little work, which means that I still remember where we were on Friday because I haven't really done anything since. So we were looking at linear programming, and we had this idea of sampling for linear programming. And the idea was eventually encapsulated in a theorem that I wrote, which I haven't yet proved. And that's going to be the first thing that we tackle today. But the statement of the theorem was, suppose that we have an LP with n constraints over dimension D. Okay. And now the claim is that if we choose a sample R of size R, and I'll use H for the constraints. If we choose sample R of R hyperplanes of H, then the expected number of violators of the optimum of that subset R is at most D times n minus R minus 1 divided by R minus D, and that's roughly D over R. Okay. And sanity check, as you increase the size, the number of hyperplanes R that you choose, the expected number of violations that you're going to see, is dn over R. The expected number of violations that you're going to see decreases, right? Which is what we would expect. Okay, and remember the idea was that any subset of the hyperplanes defines some optimum, but intuitively, at least, if you have a vertex that violates many hyperplanes, then when you choose your sample, you're probably going to pick at least one hyperplane that violates that vertex. And that hyperplane is going to prevent that vertex from being feasible, and is going to prevent it from being the optimum. So whatever vertex we end up with as the optimum of the sample, intuitively at least, it won't be able to violate a large number of hyperplanes. Okay, and so we use that in this algorithm called SampLP. Where we had a set S of active hyperplanes. And then if we don't have a lot of hyperplanes, then we would run the standard simplex algorithm, which takes d to the order d time. In this case, it's exponential in n, but there's only d squared, but n is less than d squared. Otherwise, we would pick our R. Of size d squared of n. That's our R. Okay. And then we would recursively find the optimum of R. But we'd also include all of the active hyperplanes. Okay. And then we would let V be the violating hyperplanes. And then if the size of V was less than 2 root n, then we would add V to S. And the key argument, the key to our argument was that V contains at least one new hyperplane of opt of H that is not already in our set S. Okay. And what that means is that each successful iteration adds one of opt of H to S, which means that this only happens d times, right? Because once we add d hyperplanes from the optimum to S, that means S contains all the hyperplanes of the optimum. And that means that when we recursively solve S, we find the optimum, right? So if adding a hyperplane to S only, if adding violators to S only happens d times, then this step, right, V is less than 2 root n with probability at least 1/2, since the expected size of the violating set is equal to, is equal to dn over d root n, or root n, right? So we expect not to have too many violators, and the Markov inequality tells us that that often happens. And so we have a successful round where we add hyperplanes to S. And that means, since this happens with probability 1/2, it means that in expectation, we're just going to do 2D recursive calls. For the D successes that we're looking for, right? But also, since we're only adding root n violators each time, and that means that the size of S is at most 2D, or let's see, is it 2D or 3D? Yeah, we add at most 2 root n each time. So we end up, we have at most 2D root n hyperplanes by the end, right?
Sorry, could I ask a quick question?
Sure.
Could you remind me of the argument of why V contains at least one new hyperplane of opt of H?
Sure. So the argument there was that if you had if your optimum did not hit any of the hyperplanes, did not involve any of the hyperplanes of opt of H, right? Then removing, let's see. So we're talking about the optimum of a subset, right? Which means that it is better than the optimum of the entire set because there are fewer constraints. right?
Right.
But if you think about it, if it's better than the optimum, my claim is it has to violate some constraint that defines the optimum. Because if it were better than the optimum, but didn't violate any of the constraints that defined the optimum, then it would be feasible for a set that includes the optimum constraints, right? But it's better than the best solution that can be found that obeys the optimum constraints.
Right. I guess my concern is that like you can find like you could happen to sample like a set of hyperplanes that are like in between and miss the one that corresponds to the optimum.
Yeah, but again, right? We have the optimum hyperplanes over here, right?
Right.
And and so the point is, and you can see this in 2 dimensions, right? Any point that is better than this one has to violate one of the 2 constraints that defines the optimum, right? It doesn't matter how far away I go.
Right.
I could be over here, I could be over here. I have to violate one of the constraints that defines the optimum, right? Because again, if I didn't violate any constraint that defined the optimum, then I would be a feasible point for the optimum constraints.
Right.
And if I'm feasible for the optimum constraints, I can't be better than the optimum for the optimum constraints.
Okay. Yep.
Okay. It is a weirdly circular argument. It's hard to maintain an intuition of why that's true, but the proof is very straightforward.
No, I definitely agree with that part. It's just make sure H is the set of
all the
hyperplanes, right?
Yes.
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 Okay.
Okay. Yeah. And remember that we also defined opt of H to be sort of the value of the optimum, but I should actually be more precise, since we defined B of H, the basis, to be the set of hyperplanes that define opt of H. Right?
Right. And just to make sure, V are the violators of R, right?
Correct.
But R is a random sample of H, right? Yeah.
Yes.
So my concern is, like, say you drew a line, right, in between like the dot and the other lines, right? And that happened to be your R. And like that's a violator, right? But like, and it definitely and like if R just happens to be that, right?
Yes.
Then,
well, so if you so 2 things. First of all, remember that we optimize over R union S, right? We do have these other hyperplanes that we've been collecting,
right?
And we keep them, right? But it is true, we are going to, when we choose R, like so R tells me where I'm going to find the optimum in my recursion, but it doesn't tell me which hyperplanes that optimum is going to violate, right? I mean, if this is R, if R is only one hyperplane, I can't actually, it's not enough to define a vertex, right? I'd have to choose 2 of them.
Right.
Right? And the point is that whatever 2 I choose, they're going to define a point. And if that point is better than opt, it's going to violate one of the constraints of opt.
Right.
Okay. But it can't violate any of the constraints of S because I included S in the optimization. So I won't find, so I have to find a new hyperplane that is violated, that is part of opt.
Okay, I think I'm starting to get it. It's funny, I was so on board with this last week. Sorry, it had faded from memory. Okay, thanks so much for that.
These long weekends,
yeah,
they're just murder. Okay, so again, just reconstructing the argument, right? We keep adding about root n violators each time, and we do this d times overall, so we end up with an active set of only d root n hyperplanes, right? And we also include the sample, right? So the sample size was d root n, right? That's R. And so together it's 3d root n in the recursive call. And so this let me write down a recurrence, because we're basically doing to solve this size n problem, we have 2D recursive calls that are each on a subproblem of 3D root n constraints. And then there's the extra work of checking which constraints are violated and so forth. And when you work out that recurrence, it comes out to a basic term that just comes from checking for violations, plus what the recursion costs you is log n over d squared raised to the, let me not mess it, let me not give you a big mess, right? The point is that we're pulling out a d, and each time we're taking a square root of n factor. So the depth of this thing is approximately log n, right? Because we take a square root, we take a square root of the size of the problem each time. So log n of those is going to shrink the size of the problem to something negligible. And the branching factor is d. And so that means that the runtime is about d to the log n, which is equal to log n raised to the log d power.
Can I just make sure I understand where everything in the recurrence is coming from?
Absolutely.
So for the first term, the T3D root n, that's coming from doing sample LP on R union S, and correct. R is of size d root n, and S
is a size that most, it grows to at
right,
most.
it grows by 2 root n at most each time, so it's 2d root n.
Exactly.
Okay.
And it grows by root n each time, and we only grow it d times.
Yep. And the order of d squared n, that was, I guess, checking what the violators were.
Exactly.
Why is that d squared root n?
That's just algebra, right? So in order to, you've got to check which side of a d-dimensional hyperplane a particular vertex is on. So actually, wait, maybe that's dn? Where does the d squared come from? It's evading me at the moment. It might just be dn, but that changes nothing because d is a constant. Okay, or d is small. That's what we're considering, right? The dominant term here is the log n to the log d power, right? This is something that's sort of exponential in d. So something that is quadratic in d is just not particularly important.
Okay.
Okay. So again, this is mostly just a reconstruct of where we were last time, but I did it to remind us why we care about this sampling theorem. Okay. And actually, now that I've gone through the analysis, I want to flesh out the theorem a little bit, because in our algorithm, we're not just sampling n hyperplane. We're not just sampling from our set of hyperplanes of H. We're carefully working around the subset S. So let me write this theorem revised. Okay, we're given our H of size n, and now we sample, sorry, we have an S of these active hyperplanes that we've collected. And now let's suppose that the other hyperplanes, that there are m of them, okay? And now we sample R of size R from H minus S. Okay, we're not sampling from the active set, we're only sampling from the remaining hyperplanes. Then the expected number of violations of the basis of R union S is at most D times M minus R minus 1 divided by R minus D. So the statement as I gave it at the beginning assumed S was empty. And actually, if any of you has been reading the Motwani Raghavan textbook, they only prove it for the case where S is empty. Okay, but for this algorithm, we need the more general case. Okay, and so now I'm going to prove this, and I'm going to give you one proof, which is the way it was first worked out, and is sort of the traditional proof, and it uses the same sort of clever accounting of summations that we saw in our point location data structure, where we wrote the expectation of something as a sum, we pull something out and we get a different sum, which is a different expectation whose value we know as a thought experiment, and that lets us evaluate the overall, it lets us evaluate what we care about. Okay, and so there's a certain black magic to this of knowing what summation to write and what to pull out. But I think it's informative to see how this was done. Later, I'll show you a different proof, which I at least find more intuitive. So let's I need to introduce some notation. I'm going to let C sub H be the set of all optima of subsets T union S, where T is contained in H minus S. Okay. So, you know, we're sampling a random subset of hyperplanes. It's going to be some T, and that sample, and we are going to find an optimum of that. So the optimum that we find in our sample is going to be a member of CH. Okay. Now note that the optimum of R union S is the only point violating no constraints of R. Okay. So, wait, do I have a typo there? Sorry, hold this thought. I may need to come back and fix this later, but let me go on for the moment. So now that I've defined this C sub H, let's let V sub X be the number of constraints of H that are violated by some point X in C sub H. So, you know, we consider any optimum of a subset, and we ask how many hyperplanes are violated by that optimum of that subset. Okay. Also, let I sub x be an indicator that x is equal to, the optimum of R union S. Okay. So I claim that the expected number of violators, okay, is equal to the expectation of the sum over all possible x's from my set of optima, right, of Vx, right, the event that I get, the number of hyperplanes that violate, that x violates, times the event, the indicator that x is the optimum I actually choose. Okay, so I'm now considering my experiment where I choose this random R, and I just have an indicator variable for which optimum is actually produced in that recursive optimization. Okay, and the expected value of the number of violators is just summing over all possible optima of the event that they that optimum is chosen times the number of violating number of things that optimum violates. Yes. Right. This is the most direct definition of an expectation. It's just summing over all the points in the sample space. Okay. All right. So next bit of definition. Let's let Q sub x be the number of hyperplanes defining x that are not already in S. Okay. Given that Qx, I can talk about what is the probability that I choose X as my optimum. What has to happen in order for X to be the optimum of my recursion? Well, sorry, go ahead.
You have to randomly choose all of the constraints, all of the hyperplanes defining X.
Good.
And you have to
choose, and that's the QX that I just specified, right?
Yep.
So we have to choose all QX planes defining X with S, right? Now, what else has to happen?
You have to also not choose any hyperplanes that would violate X.
Exactly. No hyperplane that violates X. Right? And how many of those are there?
Vx.
Exactly. Okay. So the probability of this event can be expressed, well, we're choosing R hyperplanes from M, so the denominator of this big thing is going to be M choose R. Just want to make sure I leave enough room here. Right? There are M choose R possible subsets that we choose. What goes in the numerator? It's the number of ways to make choices that produce what we want. Okay? So that's going to be another binomial coefficient. Okay. Now, as we said, we have to choose the QX hyperplanes that define X, right? The other hyperplanes are unconstrained. Okay. So what that tells us is Qx of our hyperplane choices are fixed, and we have R minus Qx other hyperplane choices to make. Now, how many hyperplanes do we get to choose from for these R minus Qx hyperplanes? Well, we started with M, right? But I've already told you about Qx of them that we've chosen. And I also have to rule out the violators. So is everybody happy with this formula? I've given you the number of combinations that produce X in the numerator and the total number of combinations in the denominator.
Don't you have to also do the choosing the QX planes?
No, I mean, those are fixed, right? There are QX planes that I have to take, and there's
Right.
exactly one way to do it.
Oh, right. Okay, yeah.
I'm not doing permutations here, I'm doing combinations.
Gotcha. Yep. Okay, I'm cool with this, yes.
All right, so everybody's happy with this?
Sorry, it's just a small technicality, but these are a probability that IX equals 1, right?
Yes, this is the probability that IX equals 1. IX is an indicator variable, so I can also think about it as an event. Okay. All right, so now is where we play the funny game with the math, right? I can use my rules for binomial coefficients to write this. I'm going to pull out one term or one fraction from the binomial coefficient. M minus Vx minus Qx minus R minus Qx minus plus 1 divided by R minus Q sub X times, I basically, I use this to shrink the denominator by 1. So now instead of R minus Qx, in the lower term, sorry, let me write it instead of talking, choose R minus Qx minus 1 divided by M choose R. So this is just using one of the standard identities of binomial coefficients, right? That n choose k, I can pull out an n minus k and a k and get a different binomial coefficient. Yes? And I'm now going to simplify this and just write it as m minus r plus 1 divided by r minus d times m minus Vx minus Qx, choose r minus Qx minus 1 divided by m choose r. Okay, so I simplified this. I made it smaller by because, or sorry, actually, is this an equality? No, I get equality in the numerator, and now I'm just assuming the worst case for Q sub X, right? I may have nothing that defines X, so Qx might be equal to D in the but it's never any bigger. So everybody happy with this step? So this tells me that the expected value of V, now I'm going to write, now I've got a probability for IX, so I can write my expectation, is at most, the thing that I got here, the probability, you'll notice that this is fixed. It doesn't depend on I sub X, but now I sum over all, it doesn't depend on X, but now I sum over everything and I take, you go back to this expectation up here, right? That gives me a Vx, and now I have to multiply it by the rest of I sub X, which is M minus Vx minus Qx, choose R minus Qx minus 1, all divided by M choose R. Yes? And now's where we play the same trick as we did in the point location problem. We figure out what this summation means in order to solve it. instead of actually doing the math. Okay. And my claim is that this summation is the probability that X is a point that violates exactly one constraint in my random subset R. Okay. And here's the justification for that. How do we pick a point that violates exactly one constraint in R? Well, we must pick the QX constraints that define X. And we must pick R minus QX minus 1 constraints of M minus VX minus QX that don't violate X. And then we must pick one constraint of the VX that violate X. Okay, so again, I'm looking at a particular point X, and I'm saying, what is the probability that X is violated by exactly one constraint in my random subset, in the random set that I choose? Okay. And so I have to pick what I have to pick exactly one violator, and everything else has to be just like before. I have to pick a non-violating set. I have to pick hyperplanes that don't violate X. Okay, but also, and so how many? And so the question is, how many such X's are there? Okay, I've just talked about the probability that X is a point that violates the constraint, one constraint, but how many, sorry, I skipped a step. This inner quantity is the probability that X violates exactly one constraint, and that means that the sum over X is the expected number of points in C sub H that violate exactly one constraint in R. Okay, because I've derived a formula which says the probability that X violates exactly one point in R. So if I sum over all of the points, I get the expected number of points that violate exactly one constraint in R. Okay. So what is that expectation? Well, I don't even need to think about it as an expectation anymore. If I look at my sample R, how many points that are that are defined by subsets of vertices of hyperplanes in R, how many of those points violate exactly one constraint in R? Okay, so I mean, you can't do a lot in 2 dimensions, but here's R, or sorry, R union S, not R. But here's R, and here's the optimum, right? How many of the other vertices defined by R violate exactly one constraint of R? Right? Which of these many other vertices is such a vertex? If you start at R and want to make a vertex that violates exactly one constraint, how would you find one?
Just remove the constraint.
Okay, so I could remove one constraint and say I'm willing to violate that constraint. Sorry, this is actually the optimum, right? Because we're imposed, all the constraints are imposed, and this is the optimum constraint. So when I remove one, what happens? Well, I fall down to here or to here, right? There are two places where I might go depending on which constraint I remove. Right? What's the generalization? In D dimensions, how many points are there that violate exactly one constraint?
D.
Exactly. My claim is that this is always D, deterministically. Because all you need to do is remove one constraint that you're going to violate. And then find the new optimum. And that gives you a point that violates exactly one constraint. Okay. So this whole big summation up here just turns into D.
Why can't there be multiple points that, like, that makes sense why there has to be at least one. Why can't there be two?
Well, so again, if I remove one constraint, right, that's the only constraint I'm allowed to violate. Right, so I am required to obey every other constraint. So any point that is allowed, it has to be feasible for all the other constraints, right? And how do I want to say this? The points that I'm working with are optima of subsets, right? So the only point that can emerge here is the optimum of the subset that remains, right? If it's any other vertex, it's going to have to violate at least one other constraint. And so it's going to be violating two of the constraints of my set, and I'm only allowed to violate one. Okay.
That makes sense.
And again, this relies on the fact that there can't be two optima, right? There's only one optimum, and so that's the only point that is allowed here. Okay. So, again, I'm not crazy about this proof because it's pretty opaque and requires a bunch of math, but it is correct. You can go back and check it yourselves now that you've seen it, and it produces this quantity D. It replaces this summation with the quantity D and gives us what we wanted, which was the D times M minus R over R minus D that was needed in our analysis to tell us that we ended up with not too many violators in the sample. Okay. So that
Question.
Yes, go ahead.
Could we just go back to the upper bounding of the equality into the inequality really fast? Scroll down. Yeah, could I just could you explain that again really fast, how we got from M minus V minus QX to...
So there's two things that I did. First of all, in the numerator, I just canceled the two Q sub X's, right? So the numerator is a transformation with equality.
How did you get from V of X minus V of X? Oh, it's minus V of X minus R, and then you just said V of X is equal to 0. Okay.
No, actually, you're right. So there's two things. So I cancel out the QX's, right? So what I'm left with is M minus VX minus R divided by R minus QX. So now what is the worst case, right? If I'm trying to make an upper bound, right?
Okay, yeah.
Well, I'm subtracting VX, so I'll make VX 0. And I'm subtracting QX, so I'll make QX as big as possible, which means that it's D.
Okay.
Okay?
Yeah, okay, so the numerator makes sense, and then the denominator, yep, QX, yep, cool, yep, I'm good.
Okay, so now we're done, right? So you know, again, lots of proof machinery, but the key result was this sub-exponential time, was this this simplex runtime that is only exponential in the dimension and not in the number of hyperplanes, right? Or sorry, not simplex, but this LP in time, which was like log n to the log d time. Sorry, I left out a term before, but there's the base case, right? Where you have d hyperplanes, and so you need to brute force your solution. Okay, so basically you have a solution which has a very mild dependence on n, but is exponential in the dimension. And so that was a really nice accomplishment because, again, in computational geometry, you're often working with d equal 3 or 4. And so this is just a wonderful runtime. Okay. Any questions about it? All right. Let's refine this method. Okay. I'm now going to tell you about something called iterative reweighting. So iterative reweighting is a really interesting and powerful idea, which has now shown up in machine learning, right? Under the name multiplicative updates.
Actually, quick question regarding the runtime.
Yes.
How's the violators checking time considered in this overall runtime?
Sorry, that was the other d squared n term.
Oh, okay, got it.
Right. So of course you have to be linear in n, but there's nothing else going on.
Yeah.
Okay.
Got it.
All right. So multiplicative updates. What's the idea here? In our sample LP algorithm, we generated this sample and we said one of the violating hyperplanes is part of the optimum. Okay. And so what we did was we said, well, we don't know which one. So we'll just throw all of them into our active set. Okay. And so this was very aggressive, right? Since we don't know anything, we'll just take everything. So the idea of iterative reweighting is to be more subtle about this. We're going to assign weights to the hyperplanes that represent our belief in in their being important. Which ask us how important that hyperplane is for the optimum. And of course, the answer is either it's essential, it is part of the optimum, or it's not. So the actual answers are 0 or 1. But we are going to use real numbers, and we are going to try to shift our estimates a little bit at a time so that the important hyperplanes, the ones that are part of the optimum, develop large weights, and the unimportant hyperplanes that are not part of the optimum develop small weights. And we are going to get a signal for importance by sampling. Okay, so the point is that because we're taking these little steps, it's going to be okay to be wrong sometimes, right? Sometimes we might increase the weight of an unimportant hyperplane or decrease the weight of an important hyperplane. But as long as things go in the proper direction long term, we're going to end up with high weights on the important hyperplanes and low weights on the unimportant ones. Okay. And so this is related to what's called boosting in machine learning. Okay. And the idea is going to be that when we sample, violation is going to be evidence that H is important. Right? For every violating hyperplane, we get some evidence that it is important, right? And we increase our belief that it belongs in the optimum, that it's part of the optimum. And hyperplanes that don't violate, we decrease our belief that they belong in the optimum. Okay, so the algorithm is initially we set all the weights equal to 1. Then we pick 9d squared hyperplanes with probabilities proportional to the weights.
Oh wait, so is weighting just like all done prior to the algorithm, like all the sampling and adjusting weights? We do that all prior to the algorithm, and then once the algorithm starts, the weights are fixed?
No, because my next step, right, after I pick these hyperplanes.
Wait, sorry, you started all the weights at 1. Sorry,
I start them with them all equal to 1. Now I pick some hyperplanes. Now I find the opt of that R that I picked, okay? And I find the violators, V. And now, if the sum of the weights for violating hyperplanes is less than or equal to twice the total weight divided by 9d minus 1, this is what I'm going to call a success. Okay, this is, again, I hope you see the analog to the sampling algorithm, right? If there's not too much violating weight, we call that a success, right? Then we double the weights of all the violators. And we do this, and we just repeat this until there are no violators. Right? That is, we repeat it until our sample that we optimize gives us the optimum of the entire set. Okay. And the analysis is actually quite easy. Based on a generalization of our sampling theorem. Okay, before I talked about if you sample a certain number of hyperplanes, then the number of violations is small. Now we're just going to be doing weighted sampling, and so it should be intuitively clear that the weight of violations is small. Okay, if I choose R hyperplanes proportional to weights, then the expected violating weight is at most D over R times the total weight. Okay. So again, when all the weights are numbers, what I'm saying is that if you choose R hyperplanes uniformly, then the expected number of violations is dn over R, which is what we proved in the uniform sampling theorem. Now we're just introducing weights. And you'll do this on your homework, but it's actually quite easy. You just sort of imagine that a weight of 4 represents 4 copies of the same hyperplane, right? And so now your number of hyperplanes is just the total weight, okay? So let's take that result as given, okay? That, that this is a bound on the expected number of violators. And again, if, you know, this is why I put a factor 2 in our definition of success, right? Just like in the original sampling algorithm, we now have that success has probability at least 1/2. Okay. So now comes the key. What happens in a successful, my lemma is now that after order d log n iterations, d log n successes, the optimum of H far outweighs all the other hyperplanes. And so we find opt. Okay, so again, intuition says we pick hyperplanes that violate. So we're going to frequently pick hyperplanes that are part of the optimum. So the hyperplanes that are part of the optimum are going to have their weights increase frequently. And they're basically going to outpace all of the other hyperplanes that are not part of the optimum. And so they're not going to violate as often. Okay. And the proof of this claim is that each successful iteration doubles the weight of some H in the optimum. Right? Because we've already said that whenever we look at our violating set, we get some hyperplane that's part of the optimum. Right? So what that tells me is that D successful iterations double the entire optimum weight. Right? Because in the worst case, right, if the weight of the optimum hyperplanes is all 1, right, and now I go through and double one of them k times, the worst thing that can happen is that each of them gets doubled once. Right? If I double some of them more than once, it just makes the weight bigger. Okay, and more generally, KD successful iterations increase the optimum weight to at least D times 2 to the K. Right? The initial weight is D, and each time you have K successes, it doubles. So after each time you have D successes, it doubles. So after KD successes, it will have doubled K times. And so you end up with at least multiplying the entire weight up to 2 to the K times D. Okay. Now, let's look at the other side at the total weight. Okay. Which is initially n, right? Now, what happens to that total weight on a successful iteration? Well, we add, where was that number? 2 over 9d minus 1 times the total weight to the weight, which means that we end up with 1 plus 2 over 9d minus 1 times the weight. that of the start of the iteration. So if we start with weight W, our ending weight increases by a relative factor of 2/90 minus 1. Yes? Okay, so that means after dk iterations, this weight is 1 plus 2/9d minus 1 raised to the dk times the initial weight of n. And this is an upper bound on the total weight. Everybody following? So I claim that we must stop before 2 to the kd is bigger than 1 plus 2/9d minus 1 to the dk n. Right? And this is approximately n times e to the kd over 9d minus 1, which is about n times e to the k over 9. Okay. So look at what's happening. The left-hand side is growing by a factor of 2 with k. The right-hand side is growing by a factor of e to the k over 9, which is less than 2 to the k, right? So we start with a weight of n, right, for the whole network. It starts out ahead, but it grows slowly, right? The optimum hyperplanes start with a weight of d, but they grow quickly. Okay, and so within d log n iterations, 2 to the kd is bigger than ne. Sorry, that should be in the. Within d log n iterations, 2 to the k times d is bigger than ne to the k over 9. So we stop. Okay. And that means that we only have d log n successes, which means that we only have 2d log n iterations. And each one takes d to the order of d time to optimize over 9D hyperplanes. So our runtime is simply 2D log n times d to the order d plus n for the sampling and such, and violation checking. Okay. So now we have an algorithm that's basically n log n.
So this seems to indicate that eventually you can say that the total weight of the optimum set is greater than the total weight of the entire set of hyperplanes?
Correct, which is impossible,
Yeah.
right? That's exactly the point, that if this algorithm runs for too long, we get a contradiction because the weight of the optimum has grown bigger than the weight of the entire set, but it's inside the set.
Mm-hmm. So what breaks? Why does this algorithm?
Well, what breaks is that the algorithm will choose a sample that contains the entire optimum. And at that point, the algorithm will find the optimum.
Ah, okay.
right? So basically what's happening is that the optimum hyperplanes are getting heavier and heavier. And eventually they get heavy enough that you pick them all. And then you're done.
Mhm.
Right? But this is, again, this is taking sort of more careful steps than the previous algorithm, right? It didn't say, oh, there's something optimum in this big set, I'll take everything, right? Instead it says, well, there's something optimum in this big set, but I don't know which it is, so I'll just increase all of their weights by a little bit, right? So I'm not committing to anything, but I'm just making it more likely that I take these next time, instead of guaranteeing that I take them next time.
I'm a little bit confused. Like, so I get the argument, right? But there's always a probability, right, that you can like miss.
Sure.
Right. And so like always though, so like I feel like this is like a deterministic argument, right? Like the algorithm.
It's not a deterministic argument because remember, we've got this Markov inequality in here telling us about the probability of success, right? We only do this increment in weights if the violating weight is small, right? If there's a lot of violating weight, then we don't want to do the increment because it will let the weight of the entire set run away from the weight of the optimum.
Okay, so this is saying after n success, like you can't have this many successes, and that's the important part. Okay.
This is saying you can only have d log n successes.
Okay.
And our Markov inequality tells us that that's going to happen in expectation within d log n attempts.
Okay, yeah, now I'm good.
Excellent. Okay, so any questions about this? So again, the algorithms here are very simple, right? They rely on this sampling theorem, which is not simple, or at least not simple yet. Okay, because I only showed you the complicated proof. Okay. So this was the state of the art for quite a long time, was that we had these really cool randomized algorithms that ran in time exponential in D without having a nasty dependence on N. And then along came Raymond Seidel. You may remember him. He's the guy who did the shortest paths, that mind-blowing shortest paths algorithm from matrix multiplication. And here he did something even more mind-blowing. Okay. He came up with the simplest ever linear programming algorithm, which also has the simplest ever analysis. Okay. He realized that you could apply a randomized incremental construction to linear programming. Okay. That is, you have your collection of hyperplanes. Okay, just add one at a time and update the optimum each time. And after you've added all n of them, you'll have the optimum. Yes? So all you need to do is update the optimum each time and understand what the expected behavior is in this randomized incremental construction, right? So I'm going to describe it instead recursively. What you do is, to compute Seidel's algorithm on n hyperplanes, what you do is you remove one at random. And then you recurse. Okay. And now put back the last one. So now there's two possibilities when I put back that last hyperplane. Okay. So suppose this recursion yields some x, right? So if I put back the last one possibility is that it doesn't violate x. What do we need to do in that case? We don't have to do anything. We're done. Right? Because we have this point that is optimum for all the other hyperplanes, and it also doesn't violate this one. So that means that it's optimum for the entire set. Okay? If it does violate, And let's call this hyperplane H. So now we need to fix things. Okay. But this is where Seidel had this very clever realization. If this hyperplane violates X, that means that right? This is an argument that we made before, right? If H is not part of the optimum, and that means that the optimum doesn't violate H. The only way that the optimum of everything else could violate H is if H is part of the optimum. Does everybody buy that?
I don't know if I had connection issues or you had connection issues, but you went all robot voice.
Okay, let me try this again. So my claim is that if the last hyperplane, if it violates the optimum that I found of everything else, then that last hyperplane is part of the optimum of H. Okay, and what is the reason for that? Well, if it's not part of the optimum, then the optimum is feasible for it, because that's the definition of the optimum, right? So we know that H is part of the optimum set. We have just found one of the D optimum hyperplanes. That tells us that opt is in H, is in this hyperplane. Yes?
Just to make sure, this is N is like, this is the last iteration, like we're at the very end.
We're
right?
at the very end. That is
Okay.
correct.
Cool, because like if it's before that, like, and you're removing it.
No, again, I've described it recursively because it's easier to talk about that way. So H is the very last hyperplane, and it is in the optimum set. And this is something that we never found with the other algorithms, right? The other algorithms gave us a collection of hyperplanes that contained an optimum hyperplane. But now Seidel's algorithm is definitively saying this is one of the hyperplanes of opt. Okay, now that lets me do something I couldn't do before. I'm going to project the entire linear programming problem into H. And solve it there. And what's really important here is that this is now a D-1 dimensional linear program. Right? Does anybody have trouble with the notion of projecting projecting the linear program? Right? I mean, basically you have a collection of hyperplanes, constraints, and each of them intersects with H and therefore imposes a constraint on H. So I just take all of those constraints that are projected onto H, and that defines a new polytope inside of H, which is D-1 dimensional. And now I project the objective function into that hyperplane as well. And this gives me a D-1 dimensional direction in which I want to optimize. Okay. And so once I solve it there, I have the answer, right? Because the optimum of the projection gives me the other D-1 hyperplanes that define the optimum. Okay. So very simple algorithm, very simple recurrence. If I'm given n hyperplanes in dimension D, I simply recurse on n-1 hyperplanes in dimension D. And then, well, what does happen then? Well, I might have to recurse a second time in D-1 dimensions, right? But how likely is that?
Probably D over n or something.
Why is it D over n?
Because they're most D hyperplanes H that are in the optimum.
So there's a second recursion only if the last hyperplane was one of the optimum hyperplanes, right? Which has probability D over N, right? Because I threw out a random hyperplane. So T of ND is T of N minus 1D plus, with probability D over N, T of N minus 1 D minus 1. Everybody buy that recurrence?
Does the projection take any effort at all or no?
Thank you. There's another order of dn to do the projection. Okay, or maybe d squared n. But again, it doesn't matter. Okay. And if you solve this recurrence, you get a runtime of d factorial times n. And if you plug that in, it works. Okay. So no more fancy sampling theorem. All we're using is the fact that when you throw out a random hyperplane, there's a d out of n chance that it is the optimum one. Or that is part of the optimum.
Why didn't we just start with this?
Because I wanted to give you some of the sense of how this evolved historically. Right? And I also wanted to show you the sampling, right? So the sampling techniques that we used have been surpassed in this particular algorithm, in this particular problem, but they are still extremely powerful and are used in many other algorithms. Okay.
That's fair. Makes sense.
Sure thing. Also, I wouldn't have had enough to lecture about. So, you know, I needed to fill the time.
So you have a smaller recursion with probability d over n, but how do you actually analyze this?
You mean how do I figure out that the solution is d factorial n?
No. How do you? I mean, you can't write t of n minus 1 comma d plus d over n times.
Oh, I can actually. This is an expected running time.
Okay.
And again, because of linearity of expectation, this is a valid analysis of the expected runtime.
Right. The parameters are fixed here, so it's
exactly d is fixed, right? And n is fixed as I'm doing the analysis. So yes, this is just linearity of expectation.
Thanks.
Yep. Other questions? All right. I will mention that you can use Seidel's idea to give a better, a simpler proof of the sampling theorem. Okay. So in the sampling theorem, we choose our random hyperplanes. And we want the expected number of violators. Okay. V. Right? So instead, let's consider a random hyperplane in the remaining set and ask the probability that it violates. And that is just equal to the expected number of violators divided by n minus r. Okay. right? If I choose a random hyperplane that's not in R, the probability that it is violated, that it's a violating hyperplane, is just the number of violators divided by n minus R. So the expected value of that probability is just the expected number of violators divided by n minus R. And now, separately, for the probability that H is violated, I'll just use backwards analysis like Seidel did. The probability that what I'm going to say is that instead of picking R then H, instead of picking R at random and asking about a random H, I will pick R union a random H at random together, and then randomly pick which of them is H. Okay, so everybody agree this is the same experiment? Okay, but if I pick R union H at random and then pick a random one of those to be, that is, I pick R plus one hyperplanes at random and then pick one of them at random to be H, what is the probability that it is violated? So I have R plus one hyperplanes. I choose one at random. And I ask, what is the probability that it violates the optimum of the remainder? So in this set of R plus one hyperplanes, which ones violate the optimum of the remainder? Well, time has flown, so I will simply tell you, it's the planes that are part of the optimum of this set. Right? Because any plane that is not part of the optimum is not violated if you throw it away and optimize what's left. That's what Seidel's algorithm relied on, right? So the probability that H is violated is just equal to D over R plus one, because there are D hyperplanes in the optimum, right? So I just take that up to the to my formula. So the expected number of violators is just equal to D over R plus one times 1 over n minus R, which is what our sampling theorem told us. Okay.
Or should it be times n minus R?
What was that?
Should it be D over R plus 1 times n minus R?
Oh, that's interesting. How did I end up with a denominator instead of a numerator? Oh, because I put it on the wrong side, right? So this formula is correct. Or sorry, no, I just did my algebra wrong, right? So this is the probability that it violate. Sorry, I'm rushing too much now. Why don't I not keep you any later, right? So I'll fill this in for anybody who wants to stay, but I'll also redo it on Monday or on Friday for those who want to leave, what I computed was that the probability of a violation was d over r plus 1, and I showed that that was equal to the quantity that I derived above, right? Which means that the expected number of violators, I just move that n minus r to the other side. Okay. All right. Sorry for keeping you over, but I wanted to see Seidel's algorithm because it's pretty awesome. Okay. All right. Oh, and I will see you on. I'll email about this, but I'm going to push out the next problem set a little late because because your current one is not due until Friday. And I'll send email about the details. See you on Friday.